Okay, question 2 on last year's final exam involved graphs of these two functions, f of x and g of x, and then we were asked various questions about some limits. Okay, I've copied those graphs on the board, and basically a lot of important stuff happens at ones and negative ones. So this point right here, it's clear on the final exam, is at -1, -1. And this point is at 1, 1. And the whole is at 1, -1. There were grid lines drawn in on the final exam that I didn't draw as I copied things onto the board. Okay, so we're looking at the limit as x approaches -1 of f of x plus g of x. Okay. So if I look over here at f, here's where x is -1. We've got a vertical asymptote, and I can see that's going to be going off to -infinity. Okay. If I look at g of x at -1, it's just 1, so that's going off to 1. So we have quote unquote -infinity plus 1. Now, if something is big and negative and I add 1 to it, that's not going to change the fact that it's big and negative, so it's still -infinity. One of the important things here is to get the correct notation. -infinity isn't a number. If you literally write -infinity plus 1, you're wrong. You're treating it like a number. Arithmetic is defined for numbers. It is not defined for infinity and -infinity. So that's why we want to use this arrow notation. Sometimes people try to use a rule of limits to say, oh, this is the limit of f plus the limit of g. It's a lovely rule of limits that applies to numbers. -infinity is not a number. If one part of your expression goes off to infinity or -infinity, you can't split things up to do arithmetic with the individual limits. That only works if all the limits involved are finite. So you can use your arrow notation. If you want to write off to the side, quote unquote is what I would say, -infinity plus 1. If you put it in quotes or if you write me a note to say, I do not mean this literally, I'm okay with that and I won't dock you points. But if you write equals -infinity plus 1 and then give me the correct answer, you're going to lose points for the notation. So do be very careful about respecting the fact that arithmetic only applies to finite numbers. Okay, that was part A. There are, I think, 5 parts on this problem. So part B, we're asked the limit as x goes to 0 from the left. So it's a one-sided limit of f of x times g of x plus 2. Okay. So if I look at where we are coming in from the left, so here's 0 coming in from the left, it looks like this is going to actually be going just to 1. G of x coming in to 0 from the left, well, actually coming in from either direction, g of x is approaching 0. Now in this particular case, all of the limits involved are finite. So I could, if I wanted to, say this is the limit as x goes to 0 from the left of f of x times the limit as x goes to 0 from the left of g of x plus 2. Perfectly acceptable. Okay. This limit is just 1 times, this is going to be 0 plus 2. 1 times 2 is going to give me 2. Okay. You'll notice, though, before I applied this rule of limits, I checked to make sure that everything involved was going to be finite, because I don't want to write out an arithmetic problem if one of the parts in that problem is not a finite number. All right, part C. We've got the limit as x goes to 1 from the positive side of g of x over f of x. So here's 1. We're coming in from the right, so g of x is approaching 1. Here's 1 on this graph coming in from the right. F of x is also approaching 1. Now those are both finite numbers, so if I wanted to, I could in fact write this is the limit as x goes to 1 from the right of g of x over the limit as x goes to 1 from the right of f of x. Not necessary to write that. Once I see that they're both going to 1, I can just jump right to it's going to be 1 over 1, which is 1. Okay, part D. D is the limit as x goes to 1 of e to the f of x. So, there's where my x is. I want to see what's f doing as we approach 1. Well, right here, here's 1. As we approach it from either side, it looks like we're going to 0. So this is just going to be e to the 0, which is 1. Notice what I employed there was this rule, that because the exponential function is continuous, I can actually pull that limit inside. So what I actually did was I said e to the limit as x goes to 1 of f of x, which is e to the 0, which is 1. Okay. Perfectly fine to write it out that way. Perfectly fine just to go right to here. Either way would be showing enough work for this problem. All right, one more to do. So part E is the limit as x goes to 1 of g of x plus 3. Now here's 1. The limit of g of x doesn't exist at 1. Okay? So I'm highly suspicious that this isn't going to exist either. Now sometimes if you're combining two different things, both of which are discontinuous, you can actually get some cancellation to go on, so you could get a limit that exists. But 3 is a perfectly continuous function. That's going to always be 3. It's not like it's going to behave differently from the left and from the right to somehow counterbalance the fact that this behaves differently from the left and the right. So the answer is this limit simply does not exist. Now, I would be fine with you simply stating that. If we want to be a little bit more explicit, what I could do is I could look at the two one-sided limits. I could say the limit as x goes to 1 from the left of g of x plus 3. Well, coming in from the left, we're approaching -1. So this would be -1 plus 3, which would be 2. And the limit as x goes to 1 from the right of g of x plus 3. Coming in from the right, we're expecting g of x to have a value of 1. So this would be 1 plus 3. This would be 4. These are not the same. As soon as the two one-sided limits are not the same, I conclude that the two-sided limit does not exist.